Welcome, everyone. My name is Sanskriti Deva. I'm a product marketing manager here at IBM Quantum, and I'm so excited to have here with us today Jerry Chow, who's an IBM Fellow and Director of Quantum Systems. Awesome. I'll hand it off to you now, Jerry.
Great. Yeah. Thank you so much, Sanskriti. And exciting to get the chance to speak to you all today on a topic that is not one that I've actually took some time to prepare this today because it's not one that we've talked about in a while, but I think is fun to talk about because I'm going to go into a little bit of history about how we got into this whole endeavor of putting quantum computing on the cloud and driving our roadmap and getting to the point that we certainly are today. Um, and I'll start by saying that there's a rich history, right, in quantum information science that we can really date back to the early 70s, and there's been significant milestones throughout this timeline where there's been impactful moments in terms of progressing the entire field forward. And from the early days of the birth of quantum information theory being driven by people like IBM fellow Charlie Bennett, right, all the way through the more recent history of what we've been doing from our quantum computing perspective of deploying systems, bringing them to the world, introducing Qiskit. Certainly, it's exciting to see just how many things have happened, and also this progression of things from a discovery science phase into development into really now more practical implementation. But what I want to talk about today is more focused into this bubble here, this green timeline, where we can kind of say is the 2010-ish through 2016, 2017 timeframe, where we really saw this transition from this age of development into more of this age of implementation. And it centers around really this milestone of putting our quantum computers onto the cloud. And maybe I'll just give a little bit more personal background about myself, right? So I recently celebrated 15 years at IBM. So I actually joined IBM right in July of 2010 as a research staff member. Um, and this was coming right out of my PhD, where I did my studies on superconducting qubits at Yale University with Professor Rob Schoelkopf. And coming to IBM was really something that I think was a little bit different at the time. I definitely was thinking a lot about the academic route, but then I ended up coming to an industry setting, and a big part of it was in my visit with an interview with IBM. Uh, they were able to. I was actually really excited to see some of the new results that were coming out. And this was the team then was led by Matthias Steffen, who had been here already since the late 2006. But they had just been able to show the ability to make a new qubit at the time and actually get really high coherence times. Certainly, at that time, one of the longer, more repeatable type of coherence times, and this was this with this capacity shunted flux qubit. Um, and so I think telling when you hear Matthias talk about the story today, it was literally they got this data probably about a couple of weeks before I had interviewed at IBM. And so, they were certainly, he was very excited to get the result. I was excited to see the results. And it really, then I joined in July of that year in 2010. At the same time, we had a real growth of the team. Right? So we had actually Chad Rigetti joined not long after I did, and then Jay Gambetta joined about 6 months after in early 2011. But those early days of IBM Quantum, a lot of it was very research focused. You can almost think of it as like we were in still this very academic model of extending technologies like at a small scale, understanding some of the underlying physics in terms of making things better. But we always had in the back of our mind like this constant focus on driving quality and driving improvements to make everything better, right? And we were always in this mode of experimentation, and maybe that's the most most fun story that I like to tell about that one is actually this brick experiment that we did, where we had gone to um, an external conference where there had been some presentations about the impact of infrared radiation on superconducting resonators, actually, and the quality of superconducting resonators. Where the hypothesis was, an experiment that others were doing, were saying that uh, that too much infrared radiation could harm the quality of the quality factors of superconducting resonators. And we thought about this and was like, okay, well, maybe that's what could be limiting us in the superconducting qubits that we were building. These are Josephson junction based, at the time, capacity shunted flux qubits. We came back and we were discussing this in our experimental setting, and one of the engineers on our team, Jim Rosen, said, "I absolutely don't believe this." And his his mind then went to say, "I'm going to prove to you that this is not true." And so he set up this experiment where he effectively took one of our qubit devices. You can see it there on the left, and he made a Teflon mold, and he made sure that all the cables that were connected into it to control the qubits could hang out. And he filled it with this black material. So this black material is actually highly absorptive microwave echosorb. And you can see in the middle, it's sitting on a hot plate curing, and the end result is effectively this brick that you see on the right. He made this behind the scenes, came to a few of us. It was myself, Antonio Corcolis, and Matthias Steffen, slammed it on one of our desks and said, "Go and test this." Um, and we did. And lo and behold, we actually, I think, proved him wrong, but proved the theory right, proved the hypothesis right, that in fact, we were being limited by this type of infrared radiation. And that we had to really worry about how to shield and protect our superconducting qubits to improve its performance. And so we had one really late night session of testing the device where suddenly we were measuring upwards of 5 or 6 microseconds in terms of coherence times, and that time that was a world record, right, for qubits of that type. And we were excited, and we soon after we were able to publish this paper. But it really goes to show kind of like, the type of experimentation that we were dealing with at the time. It was very bottoms up, thinking about different things that we can try and really testing them, and driving the technology forward. A big part of also what we were doing at that time was part of this broader government program. So it's run by IARPA, and it was called the MQCO project, or Multi-Qubit Coherent Operations Project. And it was really a project that was in many ways really spearheaded, I'd say, a lot of the quantum industry as we know it today, right? Because it was really pushing on different qubit modalities to show the ability to have multi-qubit operations, basically 2-qubit gates, to show that you can characterize them and benchmark them, measure things like crosstalk, and really lay the foundations for these technologies to be built towards eventually full-scale quantum computers. An interesting thing here is actually, this is from their website today. You can see that one of their crowning achievements is actually the fact that part of the research that went in here really was in the end leveraged towards the device that ultimately we placed on the cloud. And you can see them linking directly to articles talking about our quantum computers and our online quantum computers. But another fun thing to point out is just with the impact of this program, as you can see, is some of the players that were part of this, right? That out of the Duke University team, that was actually the Jung-Sang Kim and Chris Monroe team that eventually went on to found IonQ. The UC Santa Barbara team there, actually, with John Martinez, left mid-program to go work at Google, right? The University of Copenhagen team, Charlie Marcus, was of course then later on funded by Microsoft. The Innsbruck team went on to be a startup, Alpine Quantum, and the Wisconsin team with Mark Saffin has led the neutral atoms effort into inflection. So you started to see, like, this was a very kind of seminal moment, right, of all these different technologies coming together, driving these different multi-qubit types of operations. And I'd say that, we looking back, right, we had some really, this is a slide that we gave at the very end of the program of MQCO, which was in probably early 2015, where we really went on that path of really from a small scale scaling up in very digestible steps, right? From going from 2 qubits to 3 to 4 qubits and then up to 8 qubits, in these arrangements that allowed us to, in fact, at the time, already start to test some concepts that would be, interesting tests towards, like, for example, in that time, a surface code architecture. Um, it allowed us to push the underlying performance of these devices, in a very systematic way. We were able to demonstrate coherence time improvements along the way on these devices. We also learned how to really design and model and target these devices in a very repeatable and reproducible fashion. And we developed a lot of technology in terms of how to operate them. So we made these microwave-based gates. Cross resonance was one which really has been a workhorse of a lot of our early part of our roadmap. But really, let us study these types of things to in the end, ultimately, we were able to make a very stable multi-qubit device in the range of 5 to 8 qubits that we could basically go and make reproducibly, right? And with very high performance. Now, the program for MQCO actually ended in 2015, and then there was a bit of a gap before there was going to be a potentially next project from IARPA in terms of government funding. And so it was at that time that actually given the types of devices that we were making, and they were really uh, at the time were certainly high performing, even at the scale of a few 5 to 8 qubits. We wanted to try and aim for something kind of bold, right? And a few of us got together, myself, Jay Gambetta, Matthias Steffen, Mark Ritter, and a few others, and we came up with a plan for how could we really bridge this gap between these different programs, but really also drive this forward as a signature moment for IBM. And so here I'm pulling a slide from I think it was probably we were making it late 2014 and presented it early 2015 to, at the time, our science and technology leadership, where we were proposing to build a signature moment, which we called Project Iraq. And we wanted to we were actually aiming very, very, very high. We wanted to be able to show an error-corrected qubit circuit and actually drive it onto the cloud, right? So we wanted to target end of 2016, but we wanted to actually push the envelope in terms of going towards 17 qubits at the time with these kind of surface code lattices. 17 qubits is what you needed to do a simple distance 3 memory, right? In terms of a unit cell, and we wanted to really push on this multiple fronts of being able to show this thing that could let people test the concepts of error correction, but then also we wanted to make it accessible via the cloud. Part of this was that we were getting a lot of queries from people and academic professors that have seen the progress that we've been making in the MQCO project and in other areas, and they wanted to actually test things on our qubits, from benchmarking to new algorithms and things like that. And typically, the model at that point had primarily been, if you're an experimental effort, you partner with a theory team, right? And you might be able to run with them like an experiment a handful of times a year type of thing. But we had a lot of people asking us, right, about how could they actually try things on our devices through that MQCO program, and we didn't have the bandwidth necessarily to do that. And that really was a big motivation for us to drive this cloud piece, because we felt that enabling this kind of public research access could really be a special thing, right? And so we defined this at the time. We saw that there's a signature value of demonstrating ultimately an error-corrected circuit. We wanted to, of course, drive mindshare, drive talent, be the recognized leader, and really make this kind of public sandbox in terms of getting people to use it, get demos on the system, and let people try things out, right? So from the very start, we had this in mind in terms of like how can we really scale what we had been doing really at a research setting, but in a way that we could have a broader adoption and broader exposure to what we saw as really as a stable and usable technology. And so we had this timeline at the time. I think you can see it certainly was very aggressive. So we had about a 1.5 year runway to try and target end of year of 2016 at the time to launch this whole thing on the cloud of a 17 qubit error corrected device. And we aimed high at the time. We wanted to even plan for 2 whole experimental setups which would kind of ping and pong in terms of learning from one another. One with a simpler device with an 8 qubit type of device. We're also working with a software team that we identified to try to get it online onto a cloud platform. But yeah, and then we also had the infrastructure starting to get built, right? So we had a brand new lab with a couple of cryostat systems in there and open space for a larger one to be installed. And so we presented this. We got the okay. We got the funding to make this happen. We got the right talent signed on the team to make it happen. And then of course things go absolutely smoothly, right? Uh, but of course, I think this is the part of what was so great about this project was that we set a very bold vision, and of course we have along the way you course correct. Things come up like the fridge ordering and delivery took longer than we expected, right? As we were starting to do some of the research of expanding our 8 qubit device out to 17 qubits, we were learning challenges there, right? In terms of at the time yield and frequency allocation and things like that. We're like, all right, that's going to be probably a challenge to get towards. The software team initially that we were working with certainly had challenges in terms of cycles of learning, and the initial pieces that we were building were clunky. And so, of course, we digged in. We worked on scoping things down, and we brought in a ringer, right, to really make it happen. So, on one hand, we prioritized just one setup, right, in our already built lab. We didn't worry about making a whole showcase type of lab that was going to be kind of like a deployment type of system. We focused on building up the setup within our research environment. We scoped down the actual underlying device. We said, okay, we are really making these 5 qubit devices in our MQCO style with these cross resonance gates. They work really well. They have good coherence size. Let's just call that done, and we'll prioritize using that. And then on the software side, Dario really importantly connected us with Ishmael Faro. And, he brought tremendous developer and agile experience in terms of cycles of learning and really kind of going from soup to nuts of a demo and iterating on it in a way that we could really hit our timeline. At the same time as we did this type of rescoping, what had been the 17 qubit target for the end of year 2016, we said, okay, let's bring that timeline in. And it said, if we're going to do 5 qubits, let's target May of 2016. And so that really got all the wheels in motion, and it really said, like, let's get it all together and deliver it. And so and now I can just give you a couple of, I was able to look back at some of my archives, and you can see some of the old historical elements that were happening. So this is actually the 5 qubit device that we had right before it was going into the fridge. This is Antonio Corcolis. This was probably early 2016. After we had selected the payload, loaded it into its microwave shielding and magnetic shielding that you can see there. Actually, you can see some of the EchoSword material there as part of the shielding of this device before it got loaded into the fridge. And here's our setup at the time with the control electronics that you can see are very disorganized, very much looks like a research laboratory, but using commercial off-the-shelf equipment in terms of the arbitrary waveform generators, the RF generators, and so forth. Here, a couple of the team members, Balig and Oblesh, wiring up the device in the fridge, and then we're closing it all up before we cooled it down, right? And so, that spring of 2016, or that winter into spring of 2016, really was when we were testing from the hardware side, testing the device, and finding that it was really performed quite well, right? So this is another old slide that we showed at the time when we were doing a review of our progress, but basically it was 5 qubits coherence times at the time of in the 50s to 70 microseconds, which certainly were records, right, for these types of devices of that scale at the time. And then we were planning on how we were going to launch it, right? And here was where we were working with Ishmael's team on developing the initial models, right, of how to release this to our users, right? And so from this framework of what's controlling the quantum API right at the chips level, parallel path with a kind of virtual simulation type of model, connecting to a real-time API that is then exposed to the user through a web client. And we have some early screenshots here actually of this was initial iterations of the composer. At the time we didn't even call it composer. You can see it's called Playground. But with drag and drop gates and the type of execution results of block spheres for each, or projections of the distribution of results and so forth. And then of course when we did finally launch in 2016, this is what it in May of 2016, this is what it ended up looking like, right? With we added on certainly a little bit more design flair, but we're able to get this now well-known composer. We named it the IBM Quantum Experience. It came with an allocated set of usage credits, right, at the time that everyone could use. We needed we needed to add that in order to in some way manage, right, the workloads in queuing time, right, that might come up. And so some initial limitation of how many circuits people could really run on it. It's funny how even today, right, that's still some of the challenges that we deal with in terms of usage and allocation of efficiency and things like that. But really, we were already starting to plan for that all the way back then, even before we launched in 2016. And we launched it with a whole bunch of content at the time. We had a user guide. We had it is actually a picture I took off my phone. I couldn't find the screenshot of the initial introduction letter, right, that we launched it with. But I remember, it was May 4th, 2016. We launched it, I think, at midnight, and Jay and I were sitting at our computers, and we were just waiting for jobs to start coming in. We were testing it ourselves as well, but as jobs were coming in, making sure that they're running through the whole API and actually getting to the hardware, executing it, and literally almost hand watching every one of the jobs, making sure that they were actually executing. And what was to me still amazing is just how people picked it up, right? That within days, people were talking about it and tweeting about it, about testing the device and using it. We saw active engagement in terms of the community, that even the small community that we were building at that time. We quickly built up a large number of users, and the tens of thousands within a few months, right, and running a lot of different codes. We started to build in an actual community platform at the time, right? This is the early days of still driving discussion and discourse through forums, right? And so we had this community forum that many of us were active on. You can see, posting from myself and from Jay, and anybody was basically on there asking questions, and it was really exciting to have that level of engagement. And then we started seeing usage of this, right, across um, workshops and hackathons and exercises that we're starting to leverage it to test concepts of using quantum gates and coherence times, understanding how to make entangled states, and of course the community pickup beyond that led towards even research pickup, right? And this is a slide from back then. I think it was near the latter part of the year when we were really excited about 15 papers using it, right? And starting to this is sort of our kind of dream come true, right? That we said all these theorists want to work with us, but we don't have the bandwidth to do it, and here they were doing it, publishing papers, really kind of growing way beyond the scope of what direct theory experimental type of collaborations could lead to, by having this as a service, by having this as a exposed usable machine. Yeah, and so of course that led to one thing after the other, right? And just in terms of where we've gotten since then, I think it's just been tremendous, right? Like we introduced that in 2016. We did a fast follow the year after with Qiskit, right? Of course, drag and drop was nice. It was a good way for people to get started, but of course, in order to really turn this into something bigger, we have to introduce a software development kit, right? And so using a Python-based Qiskit integration, different layers of APIs, right, with Qiskit, and starting to really grow that community of, in the very early days, how to get started, how to learn about quantum computing, and engaging a community at that level. Then, of course, in 2019, we introduced the concept of the IBM Quantum System 1, right? As I mentioned before, that first instantiation was, let's just deploy it within a research environment. We knew, of course, that we can make this something that is deployable in any kind of environment, right? Especially towards starting to think about towards data center type of environments. And System 1 was really our effort to do that, right? To show the commercialization of this, the commercialization, the ability to commercialize this, and to deploy it in a self-contained architecture, right? With all the support services that are needed, and outside of a traditional research grade laboratory environment. Of course, we've since evolved that into even a modular and expandable, scalable system 2, right? And so now we showed metrics like this, right? Which is just amazing to see where we've gotten to from way back then, right? And in terms of our ecosystem and adoption, our IBM Quantum business network, our ecosystem there at IBM Quantum Network, with over 300 members, 60 industry clients, right, that are engaged. That research paper number, right, from the beginning of several handful to now over 3,800 research papers using IBM Quantum, using our services, using Qiskit. And then just other metrics here that you can see in terms of our impact with quantum courses, with learners, with content viewing, with the developer community. I think just speaks volumes of what we've been able to build here, right? And then certainly from the usage side, right, and the deployment side of circuits that have been run in the trillions, 3.5 trillion circuits having been run through our machines. Cumulatively 80 systems deployed in this time since 2016. Of course, today we focus primarily on 100 plus qubit devices with our utility scale machines, deployed across, in this case today, multiple data centers, one in Poughkeepsie, New York, one in the EU, in Einigen, Germany. This was a fun chart that Andrew Wack on my team just made, which is, instead of just a cumulative system count, right? Just what about this cumulative qubits that have been online at a given time over time? And you can see in those early days, several qubits as we were putting out 5 qubit devices and then 16 and 20 qubit devices. Um, and then you can see this real significant almost phase transition that you can see where in 2023, as we were introducing Eagle in a much more consistent fashion, 100 qubit devices, that we jump into this range where in the several thousands of qubits that have been online at any given time, driving ultimately this utility scale era that we're in right between 2023 and today. Um, and so that's really this was a lot of fun to talk about this historical backdrop, right, of where we started, right, with qubits online and where we are today. And so I sort of take the last part of my talk through this next phase, and I do want to touch on what we see as now our key milestones, right, that we certainly have on this path towards ultimately this 2029 goal that many of you probably have heard us put out there, right? That we want to deliver the first large-scale fault-tolerant quantum computer, and along the way, right, demonstrate quantum advantage next year, but all also rooted in this key demonstration of utility that we had back in 2023, where you see this phase change, right, of behavior of the community of what can be done using quantum computers. And so we have this detailed roadmap, right, that really tracks along, right, all the way back from the historical timeline of 2016 with those early, we'll call them the canary processors of 5 qubits, into the more recent utility phase with Eagle, and more recently Heron, as we drive towards 2029 when we want to release Starling. And so I'll spend a little bit of time just to talk through each of these key milestones and sort of what they really mean to us, and what I hope you all see means to the community in terms of where we're going to get to, right? And so in 2023 we did establish this concept of utility idea there, right, that we could use a noisy quantum computer even at the scale of 100 qubits and several thousands of gates to provide results that were outside of exact classical computation. Right? And so that's really a statement of the technology reaching a point where it can do something that is beyond your exact classical calculations, and it needs to be used in that framework as a tool to compare against the best classical approximate methods. I think this is also a fun thing to see, right? Which is that before that timeline of 2023, even as we were introducing Eagle, most of the papers that were being published, the average usage of any of the processors were still in the tens of numbers of qubits. And we draw this picture to show that if that was just going to be the progression, it'd be well into the mid or late 2030s before we hit any kind of work being used at the 100 qubit level. But as we released that utility result, as we continue to push out Eagles and ultimately Herons, we've really seen this phase transition of usage, right? And so today, the average number of qubits that are being used by external users on our Heron devices isn't in the teens, but is in fact well over 100. And because there's new research being done at that scale, that's really going to drive our behaviors forward to explore and to develop some of the algorithms at this level, as we really push on this near-term push towards quantum advantage, right? And so I think that's a key thing here. In this time frame that we're at now with 2026, wanting to work with the entire community to push this for this targeted quantum advantage. And what do we mean by quantum advantage, right? It's really that we can perform a task either cheaper, either faster, right, or more accurately using quantum computers as part of your computational workflow than using just purely classical computers alone, right? And of course, along the way here, we need to do so in a way which is with methods that establish trust in the outputs, and then also something that I think we all need to be cognizant of, that this is not just a singular moment in time. We're in this phase now where utility, right? But we're advantage demonstrations are going to happen, and classical will catch up on certain cases, right? And then we need to demonstrate another shot at advantage, and then classical might catch up, and then ultimately at some point classical won't catch up. And so this is an exciting phase to be in, and a big part of it, the enablement of that, is with the performance of the devices that we have, right? And today I'm very proud to say that we do have these highly performant quantum computers, right? That when we look at the number of qubits, when we look at the performance of scale, quality, and speed, right? That we certainly have the 2-qubit gate fidelities. We have the speed of the executions in terms of the time it takes to get even data in and out of the devices and out of the onto the classical infrastructure a lot faster than you can do in, for example, atomic or ion-based systems. And of course, this is a continuing moving window, right? And we need to continue to drive, in this lower right chart, up into the right as we want to drive the number of qubits up, but also certainly the performance and improving the error rates that we can have. And today, where we are at, we have our Heron devices. These are Heron devices of 156 qubits in our second iteration of that processor. It's a tunable coupler architecture, right? So we're not doing cross-resonance fixed frequency microwaves like we did at the very early days of the early quantum experience devices. But now, pushing on these error rates, which are in the low 10 to the minus 3, and in some cases at best gates even down into 10 to the minus 4 range. This has of course been something that we drive over time, right? In terms of improving the median entangling gate error rates, right? You see that as you can over the many devices that we've deployed, continually driving down this error rate, but with our current tunable coupler architecture significantly driving it down into this low 10 to the minus 3, and eventually we're going to get into 10 to the minus 4. And just the advantage of Heron over Eagle is very clear, right? So we had Eagle, and it was great in terms of being able to show that we can, do things at the utility scale at 100 qubits. But when we measure across, looking at things such as long chain performance, right? And so we have this error per layered gate measurement of 2-qubit error rates across 100 qubits that we really significantly drive down those errors, with Heron by almost an order of magnitude compared to Eagle. And certainly from the same level in terms of gate speed and crosstalk, driving down the crosstalk with Heron over Eagle, as well as really much shorter gate times. And from a technology standpoint, a lot of this comes from a lot of the iterations and cycles of learning that we have with engineering, right? And so we have probably the most advanced superconducting qubit packaging stack out there, right? So we make our qubit and qubits all internally, right? But we also make the entire devices internally with a lot of our semiconductor know-how, right, from our semiconductor area, where we had introduced these technologies, which are probably pretty common in the semiconductor front, right? But having them work well with our superconducting qubit devices has taken many years of learning in terms of through substrate vias, in terms of multi-level wiring, right? In terms of bump bond technologies, and getting really this advanced packaging stack to work. Of course, it's more than just the processor, right? It's also the technologies that go into a system. And here also we've really pushed on the engineering aspects of scaling this out, right? And so a picture on the left, probably very well known in terms of seeing like a chandelier with all these different coaxial cables. But really, with that kind of technology, limiting you to the tens of to 50 qubits or so within a cryogenic infrastructure. Now we can drive that up by an order of magnitude through very modular and high density flex cabling, right, and modular amplifiers and other components. And then similarly outside the cryogenic infrastructure, right? I think you saw in that early stage of even the 5 qubit device, we're talking about an entire rack of commercial off-the-shelf equipment to control just 5 qubits. And if you added up the dollars for that at the time, probably cost upwards close to almost $1 million just to control that type of one 5 qubit system. But driving down the cost and driving up the density of the control electronics, we've had 3 generations of doing that with our control electronics that are based off FPGAs. Now today with our Gen 3 electronics up to 400 qubits in a single rack. And so we're continuing to evolve, right? And so in the next phase of our roadmap, we're introducing Quantum Nighthawk, right? Just 120 qubits within a square lattice. We're still leveraging the tunable coupler architecture, but really increasing that connectivity to enable higher circuit complexity for what can be run. With this square lattice, really compared with our previous heavy hex, really reduces the total number of gates that might be needed for very complex workloads while working within the same error budget. And so, we're excited on Nighthawk. We're planning to bring that online by the end of the year. And it's something that just from a user standpoint, we know that can be very very optimal for circuits that are quite commonly used, like brickwork types of circuits, and certainly within the realm of looking at Hamiltonian simulation types of circuits, where we know for SQD we can get significant improvements through mapping onto a square versus a heavy hex. And so then of course this all ultimately drives us towards 2029, right? In 2029, we want to build this and deliver this large scale fault tolerant quantum computer. Looking at our innovation roadmap, this is where we have a number of technological milestones in the interim to really get us there. We published this paper last year, right, in Nature, right, which really said that we could do better than the surface code. You can certainly see that in the days up in that MQCO project and in the IRPA program that followed that, which was called Logic Q, we were very much in the surface code business. I think some of you had a talk, or some of you probably listened to a talk from David DiVincenzo, right, where he talked about the early days of surface code. And when I first joined in 2010, that was really the architecture to which we were building. Right? It was a known architecture in terms of how you can run the gate operations, how you could encode memories. It had a tremendous threshold, right, and in terms of a very favorable threshold performance. But from our perspective, I think as we were continuing to do experiments on the surface code, we started to realize, wow, the overhead could be tremendous in terms of the numbers of qubits that you might need and the associated infrastructure, the cooling, the electronics, everything. Orders of magnitude can make a difference here, right, in terms of feasibility versus infeasibility. And so the team really worked on, in a very co-design way with the hardware team to think about what can be more efficient codes. And they came up with this gross code, 10 times more efficient, right? Gross because it's a dozen or multiples of dozens. In this more interconnected lattice, right, where you have still nearest neighbor connectivity plus long distance connectivity. So you're having weight 6 checks, but bringing down the overhead of encoding from the surface code with similar threshold performance by order of magnitude. And really here, the idea is that modularity lets us really enable this kind of complexity at scale, right? That each module we would target allows us to have a gross code block of up to 400 physical qubits. We certainly know that we can build this, right? We've built Condor even with our cross-resonance architecture a couple of years ago with 1,000 qubits fitting into a single fridge. But then also we're introducing all kinds of new complexity, right? And so a big part of this is the technological enablement that we have underlying the processors. Heron, you can see, is a very sparse connectivity, right? This heavy hex connectivity. Loon, as we're planning for uh, in terms of its architecture, has six-way connectivity between qubits. Here, basically, you can't even identify where the connections are happening, right? It's really starting to look like a much more modern electronic design flow that needs to be used, right, to actually lay this out appropriately. And we're leveraging those techniques to build Loon, Kookaburra, etc., and beyond. And we're already making strides there, right? And so we're excited to try to place all these pieces together. We've already demonstrated at a lower level degree 6 connectivity without loss of gate fidelity. We need, because of those longer range, longer distance connections within the Loon device that might use multi-level wiring. We need to extend the range of these on-chip gates. We need to use what we call C couplers that leverage higher connectivity, multi-level wiring within the qubit plane stack, right? That lets us show the ability to do gates between layers, right? That leverage gates that are non-nearest neighbors. And also concurrent with this, we're working on the software side, the decoding, right? That can work within real time, right? And we have this new paper out that shows a relay architecture, relay with belief propagation that can keep up with the gross code in the cycle times that we need for operating it. And so we've for Starling, right, and towards BlueJay, we've built this fault tolerant modular architecture. We basically built it out of having multiple logical memory blocks that are connected together through that are operated on with logical processing units. There's universal adapters with L couplers that allow us to modularly connect them. They also need to modularly connect to a magic state factory. And so then this really lays out the pieces in terms of technology of what we're building towards in our roadmap, right? With Loon, really showing first the ability to have a bunch of those technologies all together. With Kookaburra, building out a logical memory with a logical operations within the memory block. With Cockatoo, connecting multiple modules of memory blocks. And then with Starling, introducing magic state factories to build towards that fully universal computational quantum computer. And so really that's the technology that we're driving towards, right? 2029 is this North Star for us for Starling, deployed 2 users, 100 million gates, 200 logical qubits, and then ultimately even with 2033 for BlueJay, 1 billion gates and 2,000 logical qubits. We are excited about this. We're already building the space for this, right? So this is what we expect that Starling will look like within our data center environment. This is our quantum data center that we newly inaugurated up in Poughkeepsie. It's a real space, right? Although this is a render, the top right system 2 is already active. And in fact, we have multiple Herons that are running on the cloud today, already deployed within there. But you can see that the space is going to expand. This is where we're going to locate Starling and ultimately, BlueJay. And so, with that, I'm really excited about everything that we have coming. I'm excited to have been able to tell you about a little bit of the history of cloud quantum computing with what we did with the quantum experience. And I'm happy to take any questions you might have.
Awesome. Thank you so much, Sherry. I know it was really insightful for everyone to hear about the journey from 15 years ago to now. So, one of the top questions that we have is, do you have any advice or steps for people to take who want to get into the hardware aspect of quantum computing, especially if they're doing like an undergraduate in engineering right now?
Yeah, so I mean, like, certainly there's um from the hardware side, there's a lot of engineering happening now today, right? And so what was, I'd say, previously primarily just in the physics realm now extends broader, right? So there's engineering in cryogenics, there's engineering in microwave uh, controls, people who do, you know, ASIC design development, right? There's a much broader scope today to get involved and have a role within this kind of, where quantum computing is going. And it doesn't necessarily mean that you need to go and get a PhD, right? So I think that's part of it. But also that you can have a very uh, broader hardware background, and still have an impact in this field today.
Wow, that's really exciting to hear. And then we had another group of questions that was asking, how do you see the role of startups within our ecosystem and the overall IBM quantum network as we move towards Advantage?
Yeah, I think it's a great question. I think a big part of that is, we can't do this all alone, right? In fact, we love our quantum ecosystem. We love our network, especially the startup members, because uh, they are building on top of the platform, and they're building within the Qiskit stack. A lot of them are developing new algorithms, developing new application functions, right, as part of our Qiskit functions platform. Um, and especially for quantum advantage, right, to use these machines to push beyond what you can do classically, it's totally ripe, right, for startups to try, insert, do things that we just don't have the bandwidth to necessarily do. Um, uh, but we bring in these high performance tools to make it happen.
That's really exciting. We're really uplifting the ecosystem in that sense then. And then we had this question pop up. You mentioned classical catching up with quantum. Could you elaborate on that? And in the future, will quantum computers be replacing classical computers?
Yeah, so I think a big part of this quantum advantage push, right, is that as we solve problems using quantum, right, and in the end, when we solve problems with quantum, we're not solving with quantum alone. We use quantum plus classical, right? Um, uh, it also gives insight, perhaps, to classical methods to improve. And so many times, classical methods then will solve a problem again, right? Maybe more efficiently. And so now you have the catch. Now quantum needs to push further again. But in terms of replacement, it certainly will never replace. I think that's a big part of this, right? That we see this completely as a um, cohesive computing architecture, right? It's what we call quantum-centric supercomputing, which is QPUs, GPUs, CPUs. They all need to work together. And in fact, we're not going to use a quantum computer to solve parts of the problem that are best suited for your CPUs or GPUs, right? And but it does handle quantum circuits and complexity of quantum circuits better than any other CPU or GPU. And so, really leveraging all three of those is really the point of view to be having.
That makes a lot of sense. So I guess we can't expect a quantum chandelier in our homes anytime soon.
Well, I
So,
mean, maybe through the cloud, right? But certainly not. I
yes,
don't think you'll need it deployed within your house.
awesome. And then the next question is, how do you define quantum advantage?
Yeah, so I think the key thing there's the way that I always say is about cheaper, faster, or more accurate. Right? Those are the dimensions to think about, right? Like especially right now, where we're doing a lot with the HPC type of community, right? Like we recently published this paper where we looked at the energy levels of iron sulfide compounds. This was in collaboration with RIKEN in Japan, and solving that problem, you can do it with high performance computers, and you can do it with Fugaku on its own, right? But even if we can do so cheaper using quantum plus classical and different classical methods, right, uh, would be an access to show this kind of quantum advantage on, right? Because in the end, users are looking for accurate results of a certain accuracy in a certain amount of time for a certain amount of cost, right? And so that's really those are the dimensions on which we can look for quantum advantage.
Great. And then our next question is, how do we maintain or service qubits and what goes into that?
Yeah, so I mean that's probably a big part of uh, my team and what we do behind the scenes. That ultimately is a big part of how we deliver these things so reliably. But a lot goes through. I mean, we do a lot of things like automated monitoring of the performance of the underlying devices. We built in a lot of things like early warning systems if things are gonna go out of bounds. We do automated recalibrations, right? And then besides that, there's also always maintaining infrastructure. So everything that people do to maintain high-end data centers, right, of GPU farms and clusters, we're doing that too for our quantum data centers, and maintaining that kind of uptime and availability to users that if they want to run a job on a Heron, that basically 99 point some percent of the time they're able to do it.
Awesome. And then a follow-up to that is what are the differences between a quantum data center and a regular classical data center?
Yeah, that's a fun question too, and especially with where we're going with current um, deployments, surprisingly not that different, right? So just as an example, we just deployed this our latest Heron in Japan, in the Riken Institute, co-located, not in the same exact building, but really, in a building adjacent to the Fugaku supercomputer. But in terms of like a lot of the underlying requirements of power or cooling water or network integration, a lot of the things that are in a modern data center are exactly what we need to put a quantum computing quantum computer into that data center as well.
Got it. And then are there any metrics that you're looking at when you're looking at the results between different quantum computers?
Yeah, so I think uh, scale, right? In terms of what is the largest circuit that you can really actually run on the across the computer. Quality of is comes down to how what accurate results can you get on that device based off on that quantum computer based off of the two cubic gate errors, based off of using noise mitigation types of methods, and then certainly speed, right? Just in terms of all these computers, quantum computers are connected classically in some way to get the data off, and any realistic problem you need to solve will end up using multiple circuits. So you need to be able to run a large number of circuits in a fast amount of time, right? So scale, quality, and speed.
Got it. Scale, quality, and speed. And then it's really beautiful to hear your story from the beginning to now. Is there anything you would tell yourself 15 years ago if you could go back in time?
I almost like wouldn't want to tell myself anything because like to me I can't believe where we are, right? Like I can't believe where we've gotten to from when I first started here, right? Like we literally were 7 to 8 people in the quarter of this building here in TJ Watson, left to our own devices to do these fun experiments, do things like that brick experiment. Um, and in many ways, it's just, keep going at it. Maybe what I tell myself, right? It's just like, uh, to me, everything that's happened has been quite magical, and unbelievable by many means. um, and just to take some of those chances like we did with putting it on the cloud, putting it out there, building it out into the ecosystem. I'd say we've been very advantageous to be sort of ahead of the game there, right? But also in many ways we've shaped this industry, right? Like a lot of fast followers that you have with the startup community, with people getting products out, getting it out into the hands of users, have all been, I'd say, part of what's made quantum such a thriving and vibrant industry today.
Awesome. And then last question. The IBM quantum processors are named after birds. Do you have a favorite bird?
Um, that's a good question. I mean, like I in the end, I like all the ones that we've named. Uh, I do really like heron. I think the herons are pretty cool. I recently was on vacation. And I saw one like chasing down uh other smaller birds. But no, they're pretty magical.
Awesome. Well, I think that's all of the time we have for today. Thank you so much to our audience for these amazing questions and to Jerry for walking us through the entire journey of IBM Quantum.
Thank you.
All right, with that.